All right, welcome back. So today we are going to be continuing our conversations on linear equations, but please first attempt this do now. It's asking you to make an input-output table for the following equation. You do not need to graph it, but I'm going to ask that you choose your inputs and receive your outputs for the function 4x plus 2y is equal to 12. I know it looks a little bit different than what we have been working with, but that is on purpose. So please choose your x's, substitute it in, receive your y's and put it as an ordered pair, and then resume when you are ready to move on. All right, if you have completed this, you should be hearing my voice. What I'm going to do is I'm going to choose 3 different x values, plug them in, and show you the y values that I get. I'm going to choose the x value 2, 0, and -2. I know that there's a 4th row there, but it's okay. So we're going to substitute in our x values into our equation. So we have 4 times x plus 2y is equal to 12. I'm actually going to put a little bit of a tech here. I'm going to clone it. Boom. Look at that. Guess what? I'm going to clone it again. Boom. Look at that. So what I'm going to do is I'm going to substitute in the x values. The first row, my x value was 2, and I'm going to solve that. Well, 4 times 2 is 8. I have 8 plus 2y is equal to 12. I subtract 8 on both sides. Then I divide by 2. I should get 2, meaning that we have 2, comma 2. Well, what happens when we substitute in 0? I have 4 times 0, which is 0. I'm left with 2y is equal to 12. I divide both sides by 2. I get 6. Therefore, I get 0, comma 6. Lastly, we have -2 was the other input that I chose. Well, 4 times -2 gives me -8. So now I have the equation -8 plus 2y is equal to 12. I have to add 8 on both sides, so I get 2y is equal to 20. I divide both sides by 2, I get y is equal to 10. Therefore, we have -2, comma 10. And again, the reason why it's in the order it is in is our x values come first. Then we have our y values that we find after substituting in those x values. Awesome. And you are probably saying, why are we looking at something that looks like this kind of equation? Well, that's a great question. Today's goal is you're going to be able to create an input-output table from an equation by converting it into what's called function form. So we had the equation 4x plus 2y is equal to 12, and today we're going to talk about how do we change that into what we have been working with when y is isolated. So we have y is equal to -2x plus 6. And this is going to be the exact same equation. We're just going to be changing the way that it looks. So without further ado, please have out your notes because we're going to be going through some guided examples. I'm going to be asking you to do a couple on your own. So here's our first guided practice example. Let's say we have 5x plus y is equal to 7. We're first going to start out, I'm going to tell you the answer to this is y is equal to -5x plus 7. So our goal here is we want to be able to isolate that y. We want to be able to isolate the y. So in order for us to do that, we have to look at our equation and say, okay, what else is on that same side of our equal sign? Just like when we had multi-step equations with variables on both sides, we had to isolate the variable. Well, it's the same thing here, except now we're trying to isolate our y. I notice my 5x was on the left with the y. I now notice it's -5x on the other side of our equal sign. So let's talk about how we get that. Well, if we want to, again, isolate the y, we need to move that positive 5x. And it's positive because there's no sign there. It's a positive 5 to it. So in order to do that, we have to subtract 5x on both sides. Well, just like before, this cancels. It goes to 0. So we're just left with y. And is 7 and -5x, or should I say, is 7 and 5x, are those like terms? No, they're not. They don't have the same variable, so we cannot combine them. So we're going to rewrite them. Now, we can have it as 7 minus 5x, or we can rewrite it as negative 5x plus 7. These are the same equations. These are the exact same equations. We just moved around the order, and we're allowed to do that with our properties of mathematics. Now, personally, I'm going to ask that we try to get this as our final answer. We want to have that variable coming first. So whatever sign we're applying it with, we want to put that in front of what's going to be called the constant. That 7 is going to be the number, right? That doesn't change. And this is, if we can establish this kind of setting now, it's going to help us later down the line, because this is actually a special form of an equation. It's called function form, but we have another pretty common name for it that we'll get to next class. But we needed to move that positive 5x over to the other side, so we subtracted it. We know that we cannot operate with 7 and 5x. They're not like terms, so we leave it. We're just changing around the order. Awesome. Let's do another guided practice, because this was more of the why. Let's show you how we actually are going to do it. So please copy down this equation. We have 8x plus 2y is equal to 12. Our goal is to isolate the y. So just like we would normally, we want to identify anything that's touching that y. Well, I have a coefficient of 2, but I also have another term. I have that additional term of 8x. Well, I don't want that 8x on the same side of my y. I see it's positive, so I know I have to subtract 8x. What I do to one side, I do to the other. This cancels out. It goes to 0. We're now left with 2y is equal. Again, I'm going to throw the variable first, because we want to get in the habit of throwing that variable in first, plus 12, because this 12 is positive, so we're adding 12. Well, this is great so far, but we didn't isolate the y. We're going in the process to get that y isolated, but we haven't done it just yet. I have 2 times y. Well, in order for me to cancel out the multiplication, I have to divide. So I divide by 2. And what we do to one side, we do to the other. So here's how we are going to work with this. We have to divide every single term by 2. We have to divide negative 8x by 2. We have to divide 12 by 2. When we do that, these 2's cancel out. We're just left with y. Well, negative 8x divided by 2 is negative 4x. Positive 12 divided by 2 is positive 6. Therefore, our equation becomes y is equal to negative 4x plus 6. The biggest thing that we see students mess up with is this spot right here, is this. Students forget that they have to divide every term by the number, or multiply every term by the number. It's very similar to the distributive property. If I had 2 times x plus 3, well, I wouldn't just send the 2 to the x to get 2x plus 3. That's wrong. We don't do that. We distribute the 2 to both of the terms. So 2x plus 6. That's right. Well, it's the same thing here, except now we're dividing. We're not multiplying, we're going to be dividing. I know there aren't parentheses, but it's the same general concept here that we want to apply to every single term within our equation. So we divided everything by 2. We get y is equal to negative 4x plus 6. And now this is a heck of a lot easier for us to use an input-output table for. Awesome. So I'm going to ask that you work on this one on your own, and then resume when you are ready to move on. All right, if you listen to my voice, that means you are ready to move on, because you try this out on your own and you're ready to check your answer. So we want to isolate the y. I notice I have an additional term of 3x. I don't want that 3x there, so I have to bring it to the other side. In order for me to do that, I have to subtract 3x. I also see some students put what we're adding or subtracting over here, and that's totally fine. That's totally fine. If this helps you realize that these are not like terms, go for it. Go for it. It's whatever you feel is best. So now we have 6y is equal to, we put the variable first, negative 3x minus 9. And again, it's minus 9 because we have the negative sign right there. That's how it correlates. Okay, we want to get that y all by itself, but I have 6 times y. So how do we get rid of it? That's right, we divide. What we do to one term, we do to all of our terms. So now our y is isolated, and we do negative 3x over 6, which simplifies down to negative 1/2 x. The fraction 3 over 6 can get divided by 3, which is 1 over 2. And now we have negative 9 over 6. This is going to be negative 3 over 2. And again, we can simplify it down. 9 over 6 can get divided by 3. We can simplify that fraction to get 3 over 2. So therefore, we get y is equal to negative 1/2 x minus 3/2. If you cut it as a decimal, for right now, that is okay. We will want to keep it as fractions when we move forward, but for right now, with your first example that you tried out on your own, if you had a decimal, that is totally fine. But let's try to get in the habit of having our fractions, because fractions are friendly, decimals are not. Let's try one more on your own. We want to isolate a y for 2x plus 2y is equal to 6. Pause the video and attempt it, and resume when you're ready to move on. All right, if you're listening to my voice, that means that you have tried this problem and you're ready to see the solution to check your work. Well, just like before, we want to isolate our y here. We want to look for any additional term. Well, we have a positive 2x here, so we're going to subtract 2x on both sides. Well, what we do to one side, we do to the other. We now have 2y all alone is equal to, oh, there we go, come on, there we go. Negative 2x plus 6. Again, we still want to try to isolate that y, but it has a coefficient of 2. So in order to cancel out that multiplication, we have to divide everything by 2. Again, this is a common error where students forget to divide everything by the coefficient. When we do that, we get y is equal to negative 2 over 2 is negative 1x. Positive 6 divided by 2 is positive 3. Now, since we are more skilled in our mathematical analysis and writing, we're actually going to leave it as negative x plus 3. And this is going to be our final answer. And the reason being is we don't write 1x. We also don't write negative 1x. We want to get in the habit of being able to identify that negative 1x is the same thing as negative x. Great job, folks. And one last question for you. Which equation would be easier to graph using input-output tables, and why? Would it be the equation written in blue, y is equal to 2x plus 3? Or would it be the equation written in that brown kind of color, negative 6x plus 3y is equal to 9? I really want to know what you feel would be best. Which equation would be easier to graph using input-output tables, and why? So please leave your answer below. All right, so hopefully we were able to identify that our blue equation would be easier to graph with input-output tables. And here's why. We have our x on one side of our equal sign. So when we plug in a value, we're going to automatically find a y value. If we plug in our x value over here on the left, well, then we would get a term with the variable of y, which means we have to move items over to one side or the other, and then we have to perform all these more operations. It's going to be a lot easier for us to work with what we call a function form. And again, it has another special kind of name to it, but we'll talk about that later when we have our y isolated. Great job, folks. If you have any questions, please jot them down. I'm really proud of you. You're doing so well, and you're working hard. Keep up the great work, folks. Have a good one.